Welcome back, everyone. Today, we'll take a closer look at some applications of AI in computer vision and natural language processing. Then, we'll ask a scary question: what if AI succeeds? In this course, we have mostly covered the foundational methods used in AI. We have talked about search, we have talked about perceptrons and how to build a neural network. We have illustrated these foundational methods with simple examples. We have not focused on the advanced applications of these methods. Now is the time to introduce some advanced applications of AI, like computer vision and natural language processing. These advanced applications still use the foundational methods that we have studied, but there are some domain specific considerations that we need to take into account. There's also some domain specific terminology that I'll try to introduce here. First, let's take a closer look at computer vision. Advanced cameras are everywhere, taking photos and videos of every aspect of our lives. Every single day, we are posting billions of selfies and other pictures on Facebook, Instagram, and other media. I tried to find out how many pictures of sourdough bread have been uploaded since the shelter in place order in March. I could not find the answer. So I did a Google image search to find images of sourdough bread that were uploaded in the past 24 hours only. And I got about 800 images of sourdough bread alone. Now, seeing and describing photos is a trivial task for very young children. Why is it so hard for computers? I believe we all agree that seeing an image and understanding what's in it are two different things. Computers can easily see or perceive an image at the pixel level, but it's trickier to extract useful information from that image. For instance, in this image, there are levels of understanding. A computer may recognize that there's a cat or two in the image. It's harder to recognize that there are two cats eating from a bowl, and even harder to recognize that there are two cats outside eating from a bowl. Similarly, with this image, we can recognize a human face. We can also recognize Steve Jobs, so these are two different tasks. One of the challenges in computer vision is being able to account for different orientations of the same object in the image. Here's a cat, and here's the same cat. Lighting is another challenge. Here's a cat in the dark. And finally, occlusion is yet another challenge. Here's our cat under a blanket. So the solution is to find some way to capture the invariance in the image. We talked about that when we talked about similarity functions. Most computer vision applications involve one or more of the following tasks: object classification. What broad category of objects appears in the image? Is there a cat? Is there a dog or a person? With object identification, we try to determine which specific object is in the image. Is it Steve Jobs or Jeff or Sarah? For object verification, we try to answer a yes or no question. Is a given object in the photo? Is Diana in this photo? For object detection, we need to determine where the objects are. Where are the boundaries? Object landmark detection is the task concerned with finding the key points for the object in the photo. We may try to detect the mouth corners to determine whether a person is smiling. In object segmentation, we answer the question, what pixels belong to the object in the image? And finally, with object recognition, we determine what objects are in the photo and where exactly are they. We usually represent images as arrays where each element of the array represents a pixel. For black and white images, we use an array of binary values. Each element of the array represents a pixel, and that pixel can be on or off. Grayscale images are represented as arrays of pixel intensities. A common representation is to have a 0 represent black and 255 to represent white. Values in between represent the different shades of gray. Now, color images contain more information. There are several ways to represent colors. The RGB model is commonly used. Here, colors are obtained by adding green, red, and blue. So each color is represented by a tuple of values. For example, yellow is a mix of red and green only, and it's represented by the tuple 255, 255, 0. So we can represent each pixel by a tuple, or we can represent images as three separate two-dimensional arrays, one for each channel, one for the red channel, one for the green channel, and one for the blue channel. So each channel has its own array. Now let's talk about filters, masks, and convolutions. You'll find these three terms used interchangeably. They refer to a technique that we use to create a new image based on the old one to extract some useful information. We use filters to detect edges in the image. We also use filters to sharpen images or to remove noise from an image by blurring it. A filter is a one- or two-dimensional array that's usually smaller than our input image. The filter is centered on one pixel in the input image. It operates on a neighborhood of pixels in our input image. The filter coefficients are multiplied by the pixel values in the input image and added together. The result goes into the corresponding pixel position in the output image. Let's look at a simple example to make sense of this. Here we have a 4x4 image. We said that the filter must be centered on each pixel. Now, to make sure that each pixel in our input image is given an opportunity to be at the center of the filter, we pad our image. We add a border on each side. Now we have a choice as to what values to put in this border. We'll just add zeros. So we'll fill this with zeros. So now we'll use this new larger image as our input image, and we'll apply the filter to this larger image. Now we're ready to apply a filter. For our example, we're going to use this filter that's called the box blur. So this filter allows us basically to blur the image by taking the average of the neighboring pixels. We start with a pixel in the input image, and we apply our filter to it. So we're looking at this neighborhood of pixels, and we are applying the filter to them. So the result here is going to be 0 times 1/9 plus 0 times 1/9 plus 0 times 1/9 plus 0 times 1/9 plus 1 times 1/9 plus 2 times 1/9 plus 0 times 1/9 plus 12 times 1/9 plus 3 times 1/9. And the result goes into the pixel in the output image that corresponds to our pixel here. So this is the upper left corner pixel, and we get the 2 here. We move on to the next pixel here, and we do the same. We compute the value corresponding to that pixel in the output image. So here we have 0 times 1/9 plus 0 times 1/9 plus 0 times 1/9 plus 1 times 1/9 plus 2 times 1/9 plus 1 times 1/9 plus 12 times 1/9 plus 3 times 1/9 plus 8 times 1/9. And we get the 3 here. Now the action of applying the filter to the image is called a convolution. So this operation here We denote it by a star. This is the convolution operator. And let me show you what we get. This is an image of Tower Hall. When we convolute it with the box blur filter, we get this blurred image of Tower Hall. And here's another example with the same box blur filter. There are many more useful filters. Some are particularly used in computer vision for detecting edges. So here's a filter that's used for detecting vertical edges. Here's another one for vertical edges. This one is good for detecting horizontal edges, and so is this one. How about this filter? What do you think? Does it detect horizontal edges or vertical edges? Let's talk about where we are in object detection. Remember, for object detection, we need to determine what the objects are in the photo and where their boundaries are. We'll first look at an approach that combines HOG and SVM. HOG stands for Histogram of Oriented Gradients, and SVM stands for Support Vector Machines. Remember, we talked about SVMs a couple of weeks ago. Up until early 2012, HOG plus SVM was considered to be the state of the art in object detection. So there are two steps involved in computing the HOG. First, we need to detect the gradients. Gradients are directional changes in image intensity or color. For every pixel, we need to take the difference between the pixel and its neighbor. We saw how we can apply edge filters to the image to do that. So let's say we have this very coarse grayscale image, and here's its representation. So let's take a look at this pixel here and compute the gradients. This pixel has an intensity of 255. The pixel on its right has an intensity of 0. So we get a gradient of magnitude 255 in the horizontal direction. We do the same for the vertical direction. We have 255 and the pixel right below it has an intensity of 150. So we get a magnitude of 155 in the vertical direction. In step 2, we take all the gradients we computed in step 1 and combine them together. To do that, we divide our image into small cells. We create a histogram of gradients within that cell. The combined histogram entries from all cells are used as our feature vector. And we end up with something like this. This is a visualization of the combined histograms of oriented gradients of some input image. So this is the information contained in our feature vector. The question is, how well does it represent the input image? Are we able to detect the objects in this image based on this feature vector? What do you think? If you are given this, can you guess what object is in the input image? If you guessed bicycle, you are correct. It turns out that the HOG makes a good feature vector. And now that we have a good feature vector, we still need a training set. So we need to get some positive examples. Can you think of a way to get positive examples of, say, bicycles? Well, one way to do that is to do an image search on Google for bicycles, and you get many, many, many images of bicycles. So positive examples are easy to come by. And for negative examples, we can just pick random images. If we're picking random images, chances are they are not going to be images of bicycles. Now, a few of them will be, and we'll have errors in our training data set, but our classifier should be general enough to ignore these errors. Once we have our training data set, we can train a support vector machine classifier. We can then test our classifier, and the results will not be very good. We'll have some mistakes, some false positives. In the second round, we're going to focus on those mistakes. All the examples where our classifier detected a bicycle where there was no bicycle, these are called hard negatives. We add those hard negatives to our training data and retrain our classifier. We get a more accurate classifier. So here are some results. We have a classifier trained to detect sofas here. So actually there was one classifier for each part of the sofa. And here the classifier detected 2 sofas correctly. And here, with these 2 cats sitting on the windowsill, it detected a sofa where we didn't have one. And here it detected the sofa where we only had an armchair. And here we have some bottles detected correctly in these 3 images. But we also have some false positives here. These 3 horses were detected correctly. But here we have a cow, not a horse, and parts of an airplane. So here again we have false positives. Here our classifier is detecting people. We have 3 correct results. Here we don't have a false positive. We are failing to detect some people because they are sitting down or holding an instrument, so the classifier is not able to detect them correctly. These days we have other good approaches to object detection. These approaches work well with the large amount of images we have access to. And these approaches are based on deep learning. We have seen how to use the autoencoder to detect faces and cats. That's more object classification that did not really allow us to delimit the boundaries of the cats. Today, convolutional neural networks are used widely in object detection. The general idea is that each layer applies a convolution to the image. The main advantage of the deep learning approaches is that we don't have to come up with our own features. We let the network figure out the features.